Alright, hello and welcome to the Midterm 2 review. My plan is, I wrote down all the stuff that you're going to be tested on, potentially, and so I'm just going to go through all of them and give you an example of each. I think, or I hope that is going to work out. So let's get started. So I made you a lovely cheat sheet. I worked so hard on it, and it goes over like syntax and things that you shouldn't be forgetting. With these beautiful colors, of course. So, functions, structs, classes, lots going on in classes, of course, how to declare them, how to implement them, and then finally pointers and some notes on what it means when you use and star in different places. Sometimes it means reference, remember. Please take advantage of this cheat sheet. May it help you. Okay, so let's go and get started. So the first thing that I want to talk about is arrays and vectors, because that's the first potential topic. Technically it was the last potential topic on midterm 1, but I didn't give you anything on it. So here's my example. We're going to create, iterate through, and print out an array, same for a vector. So the idea is, remember that an array is just a box in memory with a lot of fields. So it has a bunch of spaces for the same type. And vectors, of course, can grow. It's got a heap array inside secretly, and they can grow as you wish. Okay, so deep down in memory when we draw them, it's like, here's our vector v, or our array, ARR, and it's got a certain number of things in it. Remember that the indices start at 0. All right, so let's do some stuff. So vim arrays vectors. So here is an int array of size 3. I could say, I could immediately give it all these things, and I didn't have to give it its size. It would just figure it out. Or I can give it extra space and set some of them later. Like I can say ARR of 3, let's make that 4, and ARR of 4 can be 5. That's a size 5 array. Some things I gave at the beginning, the rest I gave over here. And then similarly a vector of ints. Or how about we do doubles? Vector of doubles v equals 3.4, 2.78, 1.5, etc. And you can add things to them, to a vector. You can be like v.pushback, remember, 42, and maybe 43. Because you can make ints doubles. Why not? Alright, so we go in, we compile and run this. Absolutely nothing happens. We just make stuff so far. So, nothing happens. We haven't done anything. We've just built up the data structures. Let's iterate through and print out the array, /vector. Alright. So we'll go 4 int I equals 0, I is less than 5, I plus plus. See out array at index I, and maybe with some spaces in between. And a new line at the end, so this will print out the array. Oops. Compile, run, 1, 2, 3, 4, 5, and we'll do the same for vectors, but we can get a bit fancier, can't we? The vector knows its size. That's super nice. v.size. Go as big as you need to go. And instead of all this, you can use this notation, but it's better to use v at I. If you watch the exception lecture, you know why now. So yeah, that's super nice. It'll print out the entire vector. But you can also use the fancier for each kind of loop, range-based for loop. You can be like for int x in v. So go through everything in v, call it x. Output it. So it's going to do, oh, sorry, there are doubles inside. It converted them to ints. That's why I should have used auto. Hey, so it's working just fine, and hopefully that is a good refresher on arrays. You got to give the size up front. And vectors can grow. Okay, beautiful stuff. All right, so that's arrays and vectors. Let's keep moving. So functions, that's the first thing on these slides. So a function's always return type. That's the thing that the function is returning, if anything. Could be void. Then the name of the function. Then you give a bunch of parameters with their types and their names. It's just another way of declaring variables. And you can also give default values for some of those parameters. And you just say, use the equal sign. Be like, okay, if you didn't give me a value for this parameter, I'm going to use the default value. Okay, so that is the syntax for functions. And I'm just going to give you some simple examples like +1 and print +1. So the rest of this review is, of course, going to have a million functions in it. So it's you're going to get your fill. Don't worry. So +1 of 2 should be 3. We can make a function that just returns the number that you give it +1. So here is the argument. It's called x. It returns an int. You return x +1 back to whoever called you. And so suddenly I'm going to use 2. I'm going to plug that in for x. That is the argument. 2 is the argument. X is the parameter that gets filled in with 2 when I call this function. Okay, so it gets x +1, returns it, and it'll print back to me 3. Hey, so that's all nice. There is another kind of function that doesn't do anything, just returns, or sorry, that doesn't return anything, it just does something. And that is a void function. Okay, so remember that void functions don't have to return anything. They can't return anything. Non-void return types mean you need to give something back. A void return type I guess I want the singular, don't I? I mean that your function just does something. It doesn't actually need to be used in a larger expression. Like technically I could say +1 of 2 times 2, because I'm going to get back the 3 and make the 6 out of it. But print +1 just gets called on its own. You can't like assign it a value because it doesn't give anything back. So print +1 of 2 will print 3, maybe with a new line. Okay, so that's the main difference. Void functions just do something. They don't give back a value. So I can't be like, that makes no sense. But for this one, you can like pretend it's getting replaced with the value that it's getting back. Okay, so that is functions in a nutshell. And remember that you can think of the way that functions are getting called using the runtime stack. It's how your functions know who to return to. So in this example, let's say we're on this line, and we're going to call from main print +1, and then that'll print its 3. So main begins the program, the terminal calls main, and then we call print +1 with the x parameter being set to 2. So it has its own local variable called x inside of print +1, and once it's done, it goes back to main, and the memory gets rid of itself. Okay? So memory goes away once functions return. Stack memory goes away once functions return. And stack frames save local variables / parameters. You can think of parameters just like local variables. Okay, so that's functions in a nutshell. Did I show you this working? I think so. Yeah. So that's functions. Let's now move on to references. So on the very last page of this, I tell you the horrible stuff that ampersand, when you see it in a type, it means reference. It has nothing to do with pointers. It's technically implemented using pointers deep down, but you don't have to know that at all. It's just something weird. So you can use references in your parameters to like actually access somebody else's value. That's a thing. And that's a good example, I think. So let's make an increment function that takes a reference parameter. So we'll increment the thing that we're given to us. So remember that a reference is just an alias for another variable. It's the same place in memory, it just has another name now. So in code, you can say the following. You can be like, okay, int x is 42 maybe. So that makes our box x holding 42. And then you can say int reference. This is the name of the type. It's int reference together. You kind of read it backwards. It's a reference to an int. Int y equals x, and so this sets up the reference. And so y is a reference to x. And so it's just another name for x. It's the same box of memory. You call it x, you call it y, it's the same place. Okay? So x++ will make it 43, and then y++ will make it 44, because it's the same place in memory. Okay, so let's make an increment function that takes a reference parameter. So let's see. Reference. I don't know. The name of the variable can be blah, and it's just going to update that blah. Blah++. So blah is taken by reference. So it's going to actually affect. It's going to touch the original memory. All right, so if I say int x equals 42 and I call increment x, it will end up incrementing x itself because we're giving it x as a reference, calling it blah up here. But references can touch the original memory. It's not getting copied. And so we can be like cout x, and suddenly it's 43, which is weird. That's references. Kind of crazy, and we know what it's really doing now because we know about pointers. It's really using pointers under the hood, but its references are just pointers that are harder to mess up. Okay, so let me draw you the stack. Let me show you what's going on here. So in main, we have a variable called x. It's a local variable to main, currently set to 42, and then we call from main increment. I'll just call it inc for fun. And increment has one parameter, but it's a reference parameter, so it's not its own separate box, it's somebody else's. So int reference blah equals x, essentially. You're passing x along into blah, yeah? So really, blah is this box of memory down here, so that's why I used everything green is inc stuff. Up here in blah, we can say, or up here in inc, we can say blah and actually affect the original x. So blah plus plus is going to be like, oh, okay, I'll go to this location in memory, increment it to 43, say no more. And suddenly we have x now being 43. Okay, so that's why you see that, and that's references. Really not too bad. Okay, one more before I go get my laundry out, and this one is testing. So we never trust ourselves. You should never trust yourself as a programmer. Remember all the times that I've made mistakes in class? Yeah, it never goes away. You're always going to make mistakes. So you got to catch yourself. You got to write enough tests to make sure that things are going to be okay. Okay, so a test is sometimes called a unit test when you're testing something small. It's a piece of code, usually a function, that tests some property of your program, tests some feature of your program. You build up an answer. You call your function maybe, and you compare what you expected with what your code actually did. Okay, so you compare what you expect with what actually happened. And if that doesn't make sense, I'm going to give you another example. Don't worry. So, yeah, that's all a test means. So we're going to make a sum vector function. We're going to test that it does the right thing. So that means, like, if we had a vector v, 1, 2, 3, we expect that the sum function on v that better give us back 6, right? Make sure it does that. Make sure it gives us back 6, given this particular v. Make sure that it gives us back with an empty vector, like there's nothing there. Make sure it gives us back 0. Maybe if there's negative values, make sure that it respects a negative value. So you can make as many tests as you want to test your code. Okay, and the more the better. So we're going to write some tests now, and we're going to make this sum vector function, making sure that it works. Okay? So to test something, usually you'll have a testing function. I like to give you that one, assert true function, right? Usually I say void assert true, bool b, string description, and if b is true, you can say passed. Otherwise, you say failed. Oops. That's the idea. So now we'll make our sum vector function. So sum vector is going to take a vector and give us back its sum. So int return value, if it's a vector of ints, that is, sum vector, vector of ints as a reference. I can actually use a constant reference so that we don't touch the thing. So use a const reference to both save memory and to not actually let ourselves touch the vector. Okay, so let's make a bad sum vector function. Let's say return 0 all the time. So let's make 2 tests. So you can put these into separate functions, but I'll just be lazy. So test 1, empty vector. So here's my v. It's empty. I want to ensure that ensure that some vector of v is 0, and that one will actually pass, right? I implemented it badly, just good enough, though, that it'll pass that one test. And that's why you have multiple. All right, so now we'll say, I can actually just push back to v if we wanted to. Why not? Let's just add some more vectors to main. So let's do v2, and make sure that the sum there is 6. And one more with maybe some negatives. You can make like -2. So now it's going to be 2, right? Okay, so, and oops, this needs to be v3, v3. So those last two should fail now, which is great, because that means we have tests that are correct and are going to do something right. So here we go. Let's actually implement some vector properly now. And bam, do we have passing tests. That is a sight to see. So that is testing. You just want to remember to compare what you expect to have happened with what actually happened. So you're going to build up like a problem that you know the answer to. Okay. I just want to unitalicize that, please. So that's the idea. Testing. Okay. So before we go on to structs, I need to put my laundry in the dryer, so I'll be back. All right, done with testing, time for structs. So here's my example. We're just going to return multiple things at the same time. That's one thing that structs are good for. Just remember that a struct is when you make a complicated type. A struct creates a brand new type made up of other existing types, potentially including the one you're just making. Fields of any type. So if I want to return an int, a bool, and a string at the same time, I can make a struct, maybe called result, and I can say it'll have an int field, it'll have a bool field, and it'll have a string field, and it'll hold all those things. So anytime I make a thing of result type, I will suddenly have access to, using the dot operator, I can say r.I equals 42, r.B equals true, r.S equals high. So that's what you get with a struct, and you can also do the same thing with like array-like notation, the I, the B, then the S in that order. So you can say result r2 equals 1 false empty string. Okay, you just give them an order like that. It's like array-like notation. And so this R, for example, in memory looks like this. It's a box with boxes inside, so it's got an int called I with 42, and a bool called B with true, and it's supposed to be a U and then an E, and then a string S with high inside of it. Okay, so that's what the memory for R looks like. That is a struct. So let's return an int, a bool, and a string at the same time. And if I want to do that, I'm going to have to return or include the string library so we can use strings. Don't forget that semicolon, very important. And yeah, these are all just fields, so I can make a function that returns a result. And it returns multiple things at a time by just packaging them inside of a result. Result is a brand new type that I get to use. Okay, so we can say call foo. It returns the R, so it'll set R2 to be that thing. It'll be like cout R2 dot S. You can get every little thing out of it. S, B, and I. Okay, yeah, and true is 1, remember that. So, 1 for true, 0 for false. Okay, that's structs, and remember the semicolon, you give it the name of the type that you're making yourself, and you just give a bunch of fields with, just like you would declare normal variables, with names and then types. And so everything of that type that you're making now has these fields with those names and those types inside. So those are structs, and structs were to help motivate classes because, well, sure, it's nice to have a struct counter with a count inside. That's fine, but what if we also had, like, instructions that we could give to the counter, like ink or something, that would make it so that we do c.ink, and suddenly the count is 43? That's exactly what we want here. So a class packages together data and operations. So normally we use structs just to package together data. Classes add those operations, those member functions. So member vars are the data. Member functions are the ops, the operations. And yeah, those are classes in a nutshell. Remember that you can have a constructor that always gets called. Right, as an object gets created. And remember that an object is just an element of a class type. It's a value of a class's type, so it's value of a class, I guess we can say, because a class creates a type, like counter. So let's make our beloved counter once more to like initialize our counts to 0 in the constructor. Then we'll have an ink method, and then maybe like a get count. So when we're declaring a class, we say class name, and then you have your public stuff and your private stuff, and potentially your consts. Lots of stuff going on, remember that. So, public for stuff that you want the user to see. And private is for stuff that only gets seen inside of the class. So when you're implementing the class, you can use the private stuff, but the user outside of your class cannot use it. So private stuff is only visible when you're implementing the class, when you're inside of a method. Of that class. Alright, so enough talking. Let's make our counter class. Counter.cpp. So a counter class, well, it's going to have a few things. Public, private. So the private thing is the count. We don't want the user to see the count. Usually all of your member variables are private. And so every counter now has a count inside of it by virtue of me saying, hey, there's a field called count. All right. And then public, we can give a constructor. Can give it a default constructor or just one that takes parameters. Like here's one that'll set the count to whatever the user gives along, defaulting to 0 if the user gives nothing. So that's the constructor. There's no return type for the constructor. Then we can have an inc method. So void inc takes no parameters, gives nothing back, just manipulates the class, manipulates the object of the counter class. And then finally we can have int get count, and this will return, it's a getter, it's an accessor, gives back the count. So we can do it just like that, and also it's const, because it doesn't change the object, it just retrieves information about it. That is quite separate from inc, which is going to change the object, it's going to change the count. Okay, it's going to reset it, whereas get count is just going to give back the count. Okay, so you can be lazy and just implement these inside of the class, but it's better practice to do it outside. And so when you do it outside, you gotta be like, okay, I'm about to declare and define this method. If it's a constructor, you gotta name it just like this. If it's any other thing, it has a return type first, and then the name of the method that you're implementing has to be prefixed with the class's name. You have to fully qualify that thing so that C++ knows that you're implementing a member function. Otherwise, it thinks it's just, okay, this is just the name of a normal function. It doesn't know that it's inside a class anymore. Okay? So let's go ahead and implement these three things down here. So constructor inc and get count. So the counter just sets the count to just sets the count to 0. So the idea is you could either do it here, you can be like, okay, yeah, my count for this current object is whatever C was. We set it to whatever the C that the user passes along. Or you could either do it here, or you could do it in the initializer list. Call it like a constructor. Okay. But it's better to set your member variables, if you can, in the initializer list, which comes after a colon. Okay? So that's that. And you can only give the default variables, default values once. That's why I think it's complaining. And then also you have to say whose counter method is it? Well, it's counter's counter method because it's the constructor. Okay? So then we do inc, it's counters inc, and get count is counters get count. So this one's going to do count plus plus to the current object, and this one's going to return the count to the current object. So if we were calling it on the C that I had in the example, be like counter C, set it to initially 42, then we increment it, it'll set it to 43. You can print out the c.getCount if we wanted to now. Dot, dot, dot. Okay. So here's me making counters in two different ways. I can call the default constructor. I can say C calls default constructor. So it'll use the default value for this constructor. It'll set counter equals counter's count equal to 0 because of the default value. Whereas this counter will set it to 42. Okay, so I'm calling the constructor here explicitly with the count that I want it to have initially. And then here I can increment C, act on C 3 times, same with C2. And then we can output the counts of each of these. And oops, that's not C2, it's just C. but this one's C2. Okay, so this should output 3 and 45. Beautiful. And it tells us when the constructor is called, because it's getting called implicitly. It's getting called for us. Every time we make a counter object, the constructor gets called. Okay? Okay. Well, classes in a nutshell. Not too bad, I think. Moving on to pointers now. So a pointer is just another variable. It's just a box in memory that holds the address of something else. It's just another type that holds the address. That's the kinds of things that a pointer holds, is the address of some other thing. So you have to be very explicit with the types as well. Int star pointers can only point to int variables. So just keep that in mind. The star means pointer to in a type, and if it's int star, you can only point to ints. You can't like point to doubles, things like that. The types are very, very specific. So now we can get to this fancy thing here. So when you see an ampersand in a type, like we've talked about, it means reference, not a pointer. Star in a type means pointer. So here we are declaring int star p. It's a pointer to an int. Ampersand outside a type means address of. So if you have a variable that is an int, the ampersand makes a pointer to that thing. So it's like it adds a star to its type. And address of x is an int, so this is an int pointer. Set it equal to p, and so p holds the address of x, which is 100 in decimal, or hexadecimal. And then you can use the star outside a type to dereference, follow a pointer. Okay? And there's this special null address that doesn't exist, that you'll get a runtime error if you try to dereference. So remember that. Usually pointer values are very large numbers because you've got a lot of memory in your machine. Okay, so let me draw a pointer diagram, and then you tell me with code how in the world I made it. Okay, so maybe pause the video after I do this. So here is, I'm going to tell you now that x is an int. Here is p, here is q, and here is r. Boop, boop, and boop. So if I were to make up, could be what I gave you. If I were to make up addresses and be even nicer, I can give you this. Be like, okay, x lives at address 100, so p holds 100, so does q, because they're pointing to x. P lives at address 104 maybe, q lives at address 112, and then r lives at address 120. So that means r is pointing to q, so, well, it better have been holding 112, okay? So I should be able to, the best way to understand how to draw these diagrams is to never draw these arrows first. Just make up addresses and, like, figure them out. So 100, p holding 100 means, and p being a pointer, means that it's pointing to x. Q is pointing to x, r is pointing to q. So tell me in code how in the world I would have made this. Okay, how can I do this in code? Move it over here. So first of all, what are the types of all these things? I know at least that x is an int. I have something q. What in the world is q? What in the world is p? Okay, so blank q, blank p, blank r, and then how do I initialize those, p, q, and r? Okay? So you tell me. Pause the video. Tell me what you think. Well, q, it's pointing to x. X is an int, so q must be an int pointer. Okay, because it holds the address of integers. Then p also is pointing to x, so it must be the same type as q, holds the address of an integer. Now r is special. It holds the address of an int pointer. It's holding the address of q. So that means r must be an int star star. So it points to int pointers. You see that? You don't use the parentheses though. It's just int star star, r. R is a pointer to pointers to ints. Okay? So if you wanted to get the x value from r, you'd have to dereference twice. That's no fun. So yeah, if you wanted to set x to be 43, you could say like x equals 43. You could say star p equals 43. You could say star q equals 43. Any of these are equivalent. You could also have said star star r equals 43. Okay? That's the idea. And if you wanted r to point to p instead, you'd have to give it the address of p. Things like that. Dun dun dun. So once these are set up, that's what we have. But how do we set them up is the final part of this question. So, can I? No, not really. Let me lasso them up here to safety. Come on. No, I can't get the semicolon, can I? Yeah, there we go. Okay. Up you go. That little straggler, I don't know what to do about. Come back down here. There we go. So how do we initialize q, p, and r now to make sure that they point to these things? Well, p needs to hold the address of x. Same with q. Let's say q equals address of x or q equals p. Then r needs to hold the address of q. You see that? Nothing hard about it. The arrows might trip you up. It's like, oh, maybe q needs to hold 42. No, no, no. It needs to hold the address of this place in memory, which is x. Okay? Because deep down in memory, C++ knows nothing about variable names. It just knows addresses. Okay? That's where things live in memory. All right. So that's pointers. That is pointers for us. And I think that's all I want to say there. We're going to use pointers a little bit more when we talk about the heap. And so I think that's the last thing that I gave you here. Again, it's kind of a simpler example as well, with just one thing. So keep all that in the back of your mind. Now let's use pointers a bit fancier, talking about the heap this time. So the heap is just a special place in memory where you can dynamically allocate things. On the fly. It's like, okay, I need 20 ints, etc. I need 50 bools. I need a, the user just inputted the number 42, so I suddenly need n, because that's where I saved the 42. I need n doubles all together in an array. So the heap's a special place where you can allocate stuff. You say new to get those things. To allocate something of a given type, let's say. So if I were to say new double, this expression would go to the heap and be like, okay, I need to make space for a double in memory. It's going to be 8 bytes long, and I will give you back the address of that, whoever called this, like double star p equals new double. Okay, so this is shiny and brand new, this place on the heap, and p is going to be a local variable to whatever function lived called this new. So maybe it was in main or something where p lived. It's just a local variable that holds 100 and now points to the double. And that's how you access it. You access this heap memory through p. You always go through a pointer. Okay? So new makes something new on the heap, and you can delete it just as easily with the delete. Okay? it removes either just single values or arrays. If you want to remove an array, you have to use the brackets. And if you want to create an array, you have to say new int and then brackets of the size that you want to make on the heap. Okay? So that's the heap in a nutshell. Let's make an array of a user-specified size and I guess find the median value of that. Let's see how we're doing. It's going to be a long review, but I mean, you're not required to watch any of this. You can fast forward. Heap.cbp. So let's see here. We need to find the median, definitely, of some array. Int median, int arr, and then int size, because arrays don't know their size. So we'll worry about that in a second. Be like return 42. And then in main, we need to ask the user, hey, how many things do you want to give to us? And then we'll get that back through cin. And finally, we'll then ask the user for n things after we make space. So it's int star, because new always gives back a pointer. Int star, I guess arr we can say, equals new int of size n. Okay, that's how we do it. And so now arr is going to point to, just like this is doing here, arr points to a brand new array made for us on the heap of the given size. Okay, so that's that, and then we can fill it in. We can ask the user for n things now. So we get that number from the user and then put it into arr. Okay, so then we have an array that's completely filled, and let's go and find the median. arr and the size was n. Okay, that's what we want. Let's see what we need to do to get it there. So right now, to find a median, I guess that's the last piece of this puzzle, we need to eventually figure out how many things are there. So let's assume that the array is always of a normal size, like it's not 0, because that would kind of ruin everything. So we need to find the midpoint. So the easiest way to do that is to sort the array and find the middle element, or elements if it's odd. So let's do the following. Let's use algorithm to sort. So we'll say sort arr starting at arr and then going until arr plus n. So you don't have to memorize this, that's just how it works. Oh, sorry, it's arr plus size. So from the start to the end, sort the entire array, please. And then we'll go and find the middle index. So if arr mod 2 is 1, we're in luck, else we have a bit of an issue. So here's the example. If the array looks like this, 1, 2, 3, 4, like 1, 2, 3, 4, the median of this, if it really does hold 1, 2, 3, 4, is 2.5, right? It'd go like in between, so 0, 1, 2, 3. So 4 divided by 2, that's the size, equals 2. So, but if we did it minus 1, it would have worked. So if we did 4 minus 1 divided by 2 equals 1, that would give us the left middle index. And so that index 1, and then that plus 1, 4 minus 1 over 2 plus 1 are the two indices to average together. Okay? So if it's even, we have to average together two indices. So we'll have to find int I equals size minus 1 over 2, and then we're going to average together ARR of I plus ARR I plus 1 over 2. Okay. Otherwise, we can find the middle index. And that'll be the median. So if it's of odd size, like it was 2, 3, 4, 5, 0, 1, 2, 3, and 4, how do you find the index 2? You take the size, 5, divided by 2. What do you get? 2.5. So integer division is just 2. So that's, we're golden there. Okay, so that's how you find the middle element. Okay, oh sorry, it's size mod 2, not ARR mod 2. So that, in theory, should work, and let's see if this works. So we're going to make a new array on the heap of a given size, fill it in, give back the median, and now, once we're done with the array, we can delete it. And remember, because it's an array, it's delete bracket bracket. Okay, so that's that. Let's see how many bugs I have added to this program. Let's say there's 4 elements. It's 4, 3, 1, 2. And the median is going to be, 2.5. Gosh, we need to return a double, don't we? That's what I did wrong. Let's try it with 5, though. Let's see here. 2, 4, 6, 8, and 10. The median should be 6. Cool, that one works. It should be a double, though, even if there's ints. That's my fault. So, I think if we can divide by 2.0, that will solve this problem. 5, 4, oops, sorry. We want 4, 4, 3, 1, 2, 2.5. Cool. All right, I'm happy there. So that's the heap. You can use it to make things of an indeterminate size. Like before the program starts, you don't know how big of memory you need to allocate, but once the program's running, you will eventually figure it out. Okay? You don't know how much memory you'll need before your program runs. Okay, so that's the heap. And now, I guess just briefly, I should touch on the difference between pointers and references. So a pointer holds an address, and a reference is just another name for a variable. So pointers hold addresses and must be dereferenced to do anything useful. And references don't have to be dereferenced. So references are just a simpler version of pointers. Okay, so I'm going to give you the two swap function examples. And then that should clear things up if it's still confusing. So here's swapping using references. We'll swap integers. X. So int temp equals x, x equals y, y equals temp. That swap with references, and then swap with pointers is almost the same. And remember that swapping without any of these things, like swapping with ints, everything just gets copied. And that's no fun. Now I need to star everything except for temp. And here's how you do both. So A equals 42, B equals 43, swap ref. Because they're references, you just give A and B. You don't have to make them a reference in any fancy way. You just set them equal. It's not a problem. Then we can see out A and then B. And they will have swapped. It will be 43, 42. And then we can swap them right back using pointers. Oh no. And if you're going to give pointers, you need to give the addresses of these ints. Okay, because that's how you make, from integers, pointers. You use the address of operator. Okay? It turns those integers into pointers. So that will swap them. Then they'll be back to 42 and 43. Okay, yeah, so it's actually working. First time it was 43, 42 from initially 42, 43. And then we swapped them one more time, and so obviously they're going to go right back to how they used to be. So here's what's working under the hood. We got your swap one, swap pointer, or swap ref, main, A, B, 42, 43. So first main calls swap ref to swap these guys. And swap ref doesn't actually have any memory of its own. It has references, which are just aliases for other things. So, oh, it actually has temp. Sorry, never mind. It has its own temp. But x and y are just other names for A and B. Okay? Like temp is x, y is x is y, 43, y is temp, 42. Okay, so that's swap ref. It's going to actually just make a new name for A and B. That's what references give you. And then once this returns, we're going to be back in main, so let me draw the state of affairs after that's all done. Eventually the stack is going to look like this again. We're going to be back in main with A holding 43 now, and B holding 42. So we're sitting right here, and we just called swap pointer, so now we're running this code. So swap pointer, it has many local variables, not just temp. It has x, it has y, and it has temp. X is a pointer to A, y is a pointer to B, and if these are addresses like 100 and 108, x would be holding those things. Y would be holding that thing. Okay, so it's like star x. Star x follows the pointer, gets the 43, sends it to temp. Star y equals, or star x equals star y. That's what I did, right? Star x equals star y. So go follow x. Set it to what you get by following y. So follow x. Set this place. Set it to whatever you get by following this pointer to get to that place. So set it to 42. And then set y to be, after following it, star y to be temp, which holds 43. Okay. So hopefully that makes it clear the difference between references and pointers. Pointers are real variables. They exist. References aren't. They're just other names for existing things. Okay? They just hold numbers, you know? That's pointers versus references. That's what I wanted to say there. And then just briefly, I'll give you a short example of files. Those should be pretty recent in your mind, so I don't have to talk too much about them. And then that's all I got for you. So let's read a file with a bunch of lines, and then we'll write a file containing the lengths of each line. So remember, you got to include fstream, so you have access to ifstream and ofstream for inputs and outputs, so reading and writing files. And these are really classes, and you just got to remember to open, got your .open. If you check IFS, if you pretend a variable is a Boolean, it'll check if it's still okay, like it hasn't passed the end of the file, right? And then you want to close your files once you're done reading or writing from them. Okay, so let's read a file with a bunch of lines and then write a file containing the lengths of each line. So if we had a file that was like a.txt, I don't know, it held blah, foo, bar, things like that. We would want to write a file, b.txt or something, that held 4, 3, 3, because it's 4, 3, and 3, and that, just like that. Okay, so here's what we're gonna do. F-stream will be like ifs, stream ifs. We're gonna open up the file a.txt, because why not? Once we're done, we're gonna close it, of course, so eventually we're gonna close that. And then we're going to count each line. So get each line and get write that length to b.txt. Okay, that's the idea. So you should usually check if it's okay, like you opened it. If you haven't read a thing and it's already false, then we have issues. Okay, there's an error opening the thing. Otherwise, let's start reading. So we'll get each line from ifs, and the way that you can do this is to use a loop with reading inside of the condition. Okay, it's like get line, ifs, and line. So it'll be like string line. So while you got a line and it's actually valid, so this body will only execute if the read succeeded. It's super nice. You can also do something like while ifs get a variable s, I, d, whatever your type is. That will work as well, and it'll only execute the body if the read succeeded. So once the file's over with, it'll stop the loop. And so before we do any of this, we need to start opening our output file. So now we have OFS to write to. So we'll write a line, which is the length of the line that we just read from IFS. Okay, I hope that makes sense. So read a line from IFS, write a line to OFS. That is the length of those lines. Okay, so yeah, in essence, we did all this already. So there we go. ifs.close, ofs.close. We're done with both. And then we can return 0. So let's make an a.txt, and then we'll run this program. Okay, so we've got like a length 7 line, length 3 or 4, no, just 3. There it is. Okay, back to this now. So let's have a drum roll now. Sorry, let's see here. Yeah, actually this is correct. I don't know what this is though. Did I do something wrong there? No. Okay, so run the file. The file's program is going to open a.txt. So it opened this file and it wrote to b.txt. So we can do, let's open b.txt. Oh man, is it the same? So length 7, length 3, length 8, length 3, length 6. It checks out. All right, so yeah, that's everything. That was a marathon of topics, I know. Props to you for getting through this, but I tried to be as thorough as possible and not waste all of your time. So that is the review. Good luck on the midterm. Please come to office hours. I mean, this review session can't replace coming to office hours and asking questions about things that don't make sense to you. Please come to those, take advantage, and remember that there's extra credit. So think about doing that if you'd like. Yeah, use the cheat sheet, and I think that's all I have for you. So I'll see you later.